2014 Canadian Open Mathematics Challenge Part B. The area of a circle that passes through the points 1, 1, 1, 7, 9, 1 can be expressed as k pi. What is the value of k? So let's draw a quick sketch. So we got 1, 1 approximately here. 1, 1, 9, 1 perhaps it is here. And 7, 1 we'll put here. So this circle is going to look something like this. Something like that. Correct? So we have labeled these points. This is 1, 1 approximately right here. 7, 1 and 9, 1. So they're saying that this has a certain area, and we have to figure out that area. Okay. So the equation of any circle, right, is x minus h squared plus y minus k. Don't get confused with this k. That's just the standard format. And then equals r squared, where r is the radius. Now we have several points on the circle, so we can just substitute them in. So let's start with this one. That would mean 1 minus h squared plus 1 minus k squared is r squared. This is my equation 1. Substitute that point, and we get 1 minus h squared plus 7 minus k squared is equal to r squared, and that becomes equation 2. Then substitute that point, and we get 9 minus h squared plus 1 minus k squared, and that is r squared, and that becomes equation 3. And now we just have to manipulate these to figure out the values of h, k, and r, and then once we get that, we can easily figure out the area, which would be pi r squared, right? Area is equal to pi times the radius squared. So we obviously need to figure out the radius. So equation 1 minus equation 2, that would give us the following. These guys would disappear, so we would just be left with 1 minus k squared minus 7 minus k squared is equal to 0, because r squared minus r squared is 0. Expanding this, we get 1 minus 2k plus k squared minus 49 plus 14k minus k squared is 0. The k squareds vanish, and we are left with minus 48 plus 12k is 0. So therefore 12k is equal to 48, and therefore k is 4. Okay, not this k. I mean, I know I should have used a different variable, but you guys understand, right? I mean, I just use this because that's just the standard way it's always been written. So don't do what I did. Use a different variable to avoid confusion. Okay. Now we'll proceed and try to figure out r. I guess we can do 1 minus 3. That would give me, let's see here, 1 minus h squared minus 9 minus h squared is equal to 0. So same story, expand 1 minus 2h plus h squared minus 81 plus 18h minus h squared is equal to 0. So we have minus 80 plus 16h is equal to 0, and h is equal to 5. Okay, so now we can easily figure out r. Substitute our values for h and k there. So we got x minus 5 squared plus y minus 4 squared is equal to r squared. And then we can substitute any one of these points into this. I'll just use 1, 1. So that'll be 1 minus 5 squared plus 1 minus 4 squared is r squared. So that's what? Minus 4 squared plus minus 3 squared is r squared. So that's 16 plus 9, which is 25. And therefore r is equal to 5. Great. So now we can get the area. Area is pi r squared. So that's going to be 5 times 5 squared. Pi times 5 squared. And that's 25 pi. And that is k pi. And therefore this k is 25. And that completes number 1. Determine all integer values of n, for which n squared plus 6n plus 24 is a perfect square. Okay. N squared plus 6n plus 24 is a perfect square, so we'll just call it m squared. So I think we need to complete the square here. You guys know how to do that, right? You take half of that, so that coefficient is 6, take half of it, which is 3, and then square it, which is 9. And then you add this 9, and then you immediately subtract it. But since we have this 24 here, we can just break up that 24 into 9 and 15. And I think that should be sufficient. And that equals m squared. So these three are able to factor, and that's the whole point of completing the square. So then we get n plus 3 squared plus 15 is m squared. Okay. So what do we do now? This n plus 3, I'm just going to call it x. So this guy here, we'll call it x squared plus 15 is equal to m squared. And therefore, 15 is equal to m squared minus x squared. So 15 is equal to, you can factor this very nicely, x plus minus. Okay, so now this is where the fun begins. How can you get 15 as a product of two numbers? Well, you can either have 15 and 1, or you can have 1 and 15, or you can have 3 and 5 and 3. I think those are the only integer solutions, because we're always talking about integers here. Okay, so let's do this one step at a time. So let's first start off with the m plus x is 15, and the m minus x is equal to 1. Okay, so if you add these two, you get 2m is equal to 16. Therefore, m is 8. Substitute that back into either of those original equations, and you get x is equal to 7. So they want the value for n, right? Well, n is this guy. N is basically x minus 3. Yeah. So n would therefore be 7 minus 3, which is 4. So this is one value of n. Okay, so now we just got to do this 3 more times. Same story. M plus x is this time 1. M minus x this time is 15. Add these and you get 2m is equal to 16. And therefore m is 8. And then when you substitute back into those, you get x is equal to minus 7 this time. And then n is minus 7 minus 3, which is minus 10. Okay, so there's another value for n. A couple more times. M plus x this time is 3. M minus x is 5. So 2m is 8, and therefore m is 4. X therefore would be minus 1, I believe. Wait, m is 4, so yeah, minus 1. So therefore n is minus 1 minus 3, which is minus 4. Okay, and then we got one more to do, and that would be the last one, which is m plus x is 5, and m minus x is 3. So when you add these two, you get 2m is 8, and therefore m is 4, and substitute m equals 4, and we get x equals 1. So n is 1 minus 3, which is negative 2. So there we go. Those are my 4 values for n. N equals 4, minus 10, minus 2, and minus 4. Five x's and 4 o's are arranged in the grid below, such that each number is covered by either an x or an o. There are a total of 126 different ways that the x's and the o's can be placed. Of these 126 ways, how many of them contain a line of 3 o's and no line of 3 x's? A line of 3 in a row can be horizontal, vertical, or diagonal. Okay. So just, I wanted to explain how you get this 126. There's obviously 9 boxes, right? So from those 9, we want to choose 5 to place the 5 x's. And from the remaining 4 boxes, you choose 4 to place the 4 o's. And when you do this, you guys know factorial notation, and 9 minus 5 factorial on the bottom over 5 factorial. And when you do this, you get 126. And 4 choose 4 is just 1. So that's how they got that 126. Okay, so they want a very specific condition here. Let's just draw this box and figure out what they want. They want you to put the x's and the o's so that you have a line of 3 o's. Okay, there's 4 o's in total. So that means you're going to put a line of 3 o's somewhere. And then there's 1 o left over, so we put it, let's say, here. And then obviously the other boxes will all be x's, right? Because they've got to go somewhere, and there's 5 of them. So this is one such scenario. That is what they want, containing a line of 3 o's and no line of 3 x's. But wait, this does contain a line of 3 x's. So that's no good. So we have to ensure that this kind of scenario does not happen. Okay. So after you fiddle around with this, you'll find that there's no way of doing it if the 3 o's are vertical or are horizontal or vertical. If the 3 o's are horizontal or vertical, you will not be able to get this to work. So the only way you can get this to work is if the o's are diagonal. So here we go again. And let me show you. So if you put the 3 o's diagonal, it fulfills the criteria that you contain a line of 3 o's. It just says line, and the line can be diagonal, so that's fine. But in this scenario, the x's will be placed in such a way that there's no line of 3 x's. So let's see, let's fiddle around with this. The o, the 4th o, we can put anywhere. So wherever you want to put it, I'll just put it here. And then watch what happens when you put the other x's. So you got x, 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 and x. You'll notice that there's no line of 3 x's. So that's the way to do this. Okay, so now that we have one way that worked, how many in total of these? Well, let's talk about it from the perspective of just going back to the beginning. I have put my o's in a diagonal, right? Okay, that's fine. Now my 4th o, I have 6 different places I can put it. I can put it either here, 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 or here. So I've got 6 spots where I can put that 4th o. And once I do, let's say I put it there, the x's just go in the other spots. They just get allotted. There's no other way to arrange them. So we really have 6 ways of doing it. But remember, there's 2 diagonals. There's one like that, and there's another diagonal that obviously is the other way, which is putting them like this. And the same kind of story, the 4th o would have 1, 2, 3, 4, 5, 6 different places that it can go. So the total, it was this 6 plus that 6, which is 12. 12 different ways to arrange these o's and x's so that you meet that criteria. Let f at x be 1 over x to the power 3 plus 3x squared plus 2x. Determine the smallest positive integer n such that f at 1 plus f at 2 plus f at 3 dot 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 plus f at n is greater than 503 over 214. Well, let's break this up first. F at x is equal to 1 over x to the power 3 plus 3x squared plus 2x. Now this denominator we can factor out an x, and then you'd get x squared plus 3x plus 2. Well, that can be easily factored further. X, let's see here, x, 2, and 1 plus, right? So that can be easily factored. Now, we're going to do a little bit of manipulation here. It's a little bit of hard work, so bear with me. This, we're going to break up into its individual factors in terms of the denominators. So for example, this guy will be something over x plus something over x plus 1 plus something over x plus 2. So all I've done there is just broken it up into its factors. Okay, so now we have to kind of mix and match here. Let's get a common denominator now. I'm going to need a lot of space here. So let's bring this over here. Well, the common denominator is already been written up there, and that's pretty obvious. Now I've got to do the top. That's going to be a times x plus 1 plus x plus 2. And then b times x plus 2. And then c times x plus 1. All right. Now we will expand this and collect like terms. And when you do, you get a plus b plus c as the coefficient in front of x squared. And then in front of the coefficient in front of x will be 3a plus 2b plus c. And then you'll have this 2a out there. And then this is, of course, over x plus 1 times x plus 2. Okay. Now, keep in mind that that is equal to 1 over x to the power of 3 plus 3x squared plus 2x. Okay. So now, looking at this, comparing these coefficients, this is just a 1. So that means the 2a is the 1. So the 2a is the 1. So that means a is a half. Okay. And then there is no coefficient over here for x squared, so that means this a plus b plus c is 0. And therefore, since a is a half, b plus c is equal to negative a half. And then similarly, there is no coefficient over here for x, so that means this 3a plus 2b plus c is 0. And since a is a half, 2b plus c is negative 3 over 2. Okay, so this one and this one I can use to figure out the values of b and c. Well, from this one we can get that c is equal to negative a half minus b. Substitute that in here and we get 2b minus a half minus b is equal to minus 3 over 2. So that means b is equal to, add a half to both sides, and you get negative 1. And therefore substitute that back into any one of these equations, and you'd get c is equal to a half. So there you go. So that basically means that this is equal to a half times 1 over x, right? Because it was this guy. B is negative 1, so I guess that's going to be a negative 1 over x plus 1. And then c was a half, so plus a half times 1 over x plus 2. There we go. So all that hard work to get this expression right here. Now we got to go back and look at this guy. So that one tells me that I've got this scenario here that f at 1 plus f at 2 plus f at 3 and so on, right? Dot, 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 until we get to f at n apparently. And that has to be greater than, what was it? 503 over 214. Okay, let's see. 503 over 214. Okay, so let's use this formula to figure out what this could be. So f at 1 is going to be 1/2 times 1 over 1. And then I'm going to actually, you might think of this being a little weird, but I'm going to actually put the next one in another bracket, and it'll kind of make a little bit sense a little bit later on. And then similarly, the last one I'll put into another bracket, this guy here. So here we go. So if you put 1 for x, you get 1 over 1, and then this term would be 1 over 2. And then the final term here would be 1 over 3. Like that. And then if you put 2, you get for this term 1 over 2. For this term, you get 1 over 3. And for the last term here, you'd get 1 over 4. So as you can see, I'm breaking it up a bit and then combining them. And then you just keep going like that, right? For 3, it would be 1 over 3. This guy here would be 1 over 4. And then this one would be 1 over 5. And then you just keep going. And then eventually dot, 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 you would get to this n. So that would be just be 1 over n. And similarly, this would be dot, 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 1 over n plus 1. And then this one, dot, 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 would be 1 over n plus 2. Okay, so I hope that made sense. Now we have to carefully, without making any mistakes, combine them. And what we're really going to do is combine the first bracket and the third bracket. So combine the terms in this with the terms in this. Okay, so here we go. All right, so carefully now. The good news is both of those brackets have a half out front, so I can factor that out. And then let's see, what can we combine here? Can we combine anything? Well, let's see. We got a 1 out here. That doesn't seem to combine with anything. Then we have a half. That also is sort of alone. But then we get some good news. We get 2 of these 1/3. You get a 1/3 here and a 1/3 here. And then it just keeps on going like that. You'll have 2 1/4. And it'll keep going like that. And then eventually, you'll have 2 1 over n's. And then you'll have exhausted everything in there. So then you'll just have from here 1 1 over n plus 1 and 1 1 over n plus 2. So that is the full combination of the first and the third. And then don't forget this guy. We got to put that in there. That's just going to be, well, for now, it'll be exactly the same. 1/2 plus 1/3 plus 1 over 4 plus dot, 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 1, all the way to 1 over n plus 1. Okay, now let's see if this gets us anywhere. So I think once we start multiplying the half, we will start getting some interesting solutions. So the half times the 1, this guy right here, is just going to be a half. A half times a half, that's a quarter. And then the rest of them, it's 2 over 3, right? 1/3 plus 1/3 times a half. So it'll be just 1 over 3. And then there's 2 over 4, but then when you multiply that by a half, it'll be 1 over 4. So you see what's happening? And then similarly, once you get down to here, it'll be 2 over n, but then once you multiply by that half, it'll be just 1 over n. And then at the very end, these guys, there's only a single of them, so it'll be 1 over 2 times n plus 1, and then 1 over 2 times 1 over n plus 2. So that's about as far as we can go there. And then this guy, I think for now, it pretty much stays the same. We're not doing much with that other bracket. But I will add in a couple, just one extra one, 1 over n, which appears right before the last term, like that. Okay, so far, hopefully this is not too bad. Now, some very interesting things happen. Some, well, you can call it magic or whatever you want to call it. Concentrating on this negative sign. The 1/2 minus a half is gone. Okay, so well, we'll just circle it. The 1/4 doesn't seem to have anything yet, so let's just put it there. But the 1/3 and the minus 1/3, right, because you're subtracting, that's gone. 1/4 will be gone with that 1/4. 1 over n will be gone with that 1 over n. And then therefore, all you're left with is going to be this and this, which would be a half minus 1, so negative a half. So negative a half times 1 over n plus 1. And then this one sort of stays exactly the same, so 1 half over n plus 2. Okay, so I did that slowly just to make sure that it didn't seem too confusing. Okay, so now we got a pretty decent and relatively straightforward equation to work with. And remember, this has to be, we almost forgot, greater than 503 over 214. Okay, so now let's work with this guy here. I think this should be without too much difficulty. 1 over a quarter, and then it's going to be, let's see here, the common denominator is going to be 2 times n plus 1 times n plus 2. And then this is going to be n plus 1 and minus n plus 2. Yeah. Put that in brackets there. Okay, so that looks like a quarter plus the n's cancel minus 1. Okay, so that basically means this is minus 2n plus 1 times n plus 2. And I guess we have to just keep going here. That's greater than 503 over 214. Should we combine this? I think so. Or actually, I have a good idea. I can just put the numbers on each side. So the 1 quarter and the 503, I'll put that on one side. And then we'll just have an equation with n's. 2n plus 1, n plus 2. There we go. Okay, well now we got to add this fraction here. This is 2014. So, oh boy. Does 2014 divide by... No, it doesn't divide by 4. Because it would be... that's okay. Just get a common denominator. 4 times 2014. So this will be 2014. And this would be 503 times 4. So that's 2014 minus 2012, right? 4 times 503 is 2012, so that's 2. And then we have 4 times 2014. So that's just going to be, let's see here. Well, let me just put these in so I don't lose them. 2 over n plus 1, n plus 2. And then I guess in cross multiply. So 4n plus 1, n plus 2 greater than 4 times 2014. Okay, we're getting somewhere. And then I guess I can factor out the 4. So n plus 1 times n plus 2 is greater than 2014. Okay, so now I guess I got to do inspection. You know, I've got to figure out what's the smallest number that would satisfy that. And you can fiddle around with this. Let's see, if n is 43, it would be 44 times 45, which is 1980. If n is, that's not greater than 2014. If n is 44, this would become 45 times 46, which is 2070. Okay, so when n equals 44, that's the first time you get over 2014. So there we go. N equals 44 is the smallest integer that satisfies the conditions.